The balanced equation from yesterday still sat on the board like it was waiting for applause.
Yesterday, we used coefficients to make the atom count match.
So the equation stopped losing oxygen and started behaving like science.
Today, those coefficients have a second job. They can describe a reaction ratio.
I knew the numbers were hiding a personality.
A ratio compares amounts. It tells how many of one thing go with how many of another thing.
Like 2 lemon slices for every 1 dramatic glass of iced tea.
Ratio example accepted, although the drama is not required.
In a balanced equation, the coefficients compare particles in the reaction.
For 2H2 plus O2 produces 2H2O, the coefficient ratio is 2 to 1 to 2.
That means 2 hydrogen molecules react with 1 oxygen molecule to form 2 water molecules.
Important question, does 2 mean 2 grams?
Not here. In this sentence, the coefficients compare particles or groups of particles, not grams.
Clarification stored. Coefficients first show a particle ratio.
And because it is a ratio, it can scale. 4 hydrogen molecules would go with 2 oxygen molecules and make 4 water molecules.
The numbers no longer looked like decoration. They looked like instructions.
So the equation is not just balanced. It is giving us a tiny recipe for the reaction.
Exactly. Our question today is, how do coefficients help us predict amounts without changing the chemistry?
Sera drew a long bracket under the equation, as if the symbols were a sentence that needed punctuation.
Before we use the ratio, we have to rate it in the same order as the equation.
The equation says 2H2 plus O2 produces 2H2.
So the order is hydrogen, oxygen, water.
Coefficient sequence detected. 2, 1, 2.
The lonely one is invisible, which feels a little rude.
In chemistry, if no coefficient is written, we understand the coefficient as 1.
Invisible one, present but shy.
That gives us the ratio 2 to 1 to 2.
2 hydrogen molecules, 1 oxygen molecule, 2 water molecules.
Good, but say the whole relationship. Do not just list the numbers.
For every 2 hydrogen molecules that react, 1 oxygen molecule reacts, and 2 water molecules form.
Complete sentence approved. The ratio order is preserved.
So if I say 2 water, 1 oxygen, 2 hydrogen, I have the same numbers but the wrong story.
Exactly. Ratio language depends on order and meaning.
The numbers only become useful when we attach them to the correct substances.
The board no longer showed a mysterious code. It showed a relationship the class could read out loud.
The ratio is not just math, it is grammar with molecules.
Perfect. Next, we will use that grammar to scale the reaction.
Theo placed 6 blue hydrogen tokens on the table and waited for someone to protest.
If the ratio is 2 hydrogen to 1 oxygen, what happens when we have 6 hydrogen molecules?
First, we congratulate them for attending as a group.
6 hydrogen is 3 groups of 2 hydrogen.
Good, the ratio unit is 2 hydrogen with 1 oxygen.
So we need 1 oxygen for each group of 2 hydrogen.
3 groups detected. Oxygen requirement, 3 oxygen molecules.
Then the water side scales too. Each group makes 2 water molecules.
3 groups make 6 water molecules.
Exactly, we multiplied every coefficient by 3. 2, 1, 2 became 6, 3, 6.
So the numbers got bigger, but the relationship stayed the same.
That is scaling a ratio. You change the amount, not the relationship.
Ratio check. 6 to 3 to 6 simplifies back to 2 to 1 to 2.
The equation grew taller, but it did not become a different equation.
Right, it is still the same chemical relationship.
So scaling helps us predict larger batches from the balanced equation. The class watched the tokens line up. The ratio was no longer just a number pattern, it was a tool.
Next, we will connect this particle ratio to the word proportional.
Sera slid an empty tray beside the molecule tokens and gave the class a very teacher-looking smile.
Now the ratio becomes useful. If we know one amount, we can predict the matching amounts.
So the ratio is not just a fact, it is a tool.
Let us start with oxygen this time.
Bold choice, oxygen has been waiting for screen time.
Known amount detected, 4 oxygen molecules.
The ratio says 1 oxygen goes with 2 hydrogen molecules.
Good, 4 oxygen groups need 4 copies of that hydrogen part.
4 copies of 2 hydrogen make 8 hydrogen molecules.
And the water part matches the hydrogen coefficient, 2 water molecules per oxygen group.
4 copies of 2 water molecules equal 8 water molecules.
So 4 oxygen asks for 8 hydrogen and gives 8 water.
Exactly, the known amount chose the multiplier.
Then the multiplier scaled every part of the ratio.
The missing amounts were not guesses, they were ratio predictions.
The empty tray was no longer empty. It had become an answer the equation could justify.
So if we change the known amount, we change the multiplier.
Yes, next we will be careful about what kind of amount we are using.
Ben slid the kitchen scale toward the molecule tokens with the confidence of someone about to be corrected.
So if the coefficient is 2, that means 2 grams, right?
Not yet, the coefficient first talks about particles, not grams.
It counts molecules in the reaction ratio.
So 2 hydrogen means 2 hydrogen molecules in the ratio pattern.
And 1 oxygen means 1 oxygen molecule in that same pattern.
Mass conversion request denied. Current unit, molecule count.
The scale has never looked so personally rejected.
The scale will matter later, but it needs a bridge.
Right now, the balanced equation gives a particle relationship.
If we call the coefficient grams too early, we mix up 2 different kinds of amount.
Exactly, particle count and mass are connected, but they are not the same thing.
So the ratio is allowed to count first.
Recommendation: do not weigh a coefficient directly.
I will apologize to the coefficient and the scale separately.
The class moved the scale aside. The molecule token stayed in the middle, where the ratio could do its first job clearly. First, particles. Later, we can learn the bridge to mass.
That bridge has a name, and we will approach it gently.
Sera wrote the balanced equation again, but this time she covered the shortcut symbols with one hand.
Before we calculate, we need to say the relationship clearly.
So not just 2 to 1 to 2.
Right, a ratio becomes more useful when we attach names to the numbers.
2 hydrogen molecules react with 1 oxygen molecule.
And they form 2 water molecules.
That sounds less like math code and more like a sentence.
Sentence frame approved. For every 2 hydrogen molecules, 1 oxygen molecule is required.
Then we can add, and 2 water molecules are produced.
Excellent, the words for every help us keep the relationship together.
For every 2 hydrogen molecules, 1 oxygen molecule reacts, and 2 water molecules form.
So the sentence carries the whole ratio, not just the first number.
Exactly, complete sentences protect us from losing one substance.
Also, they make the equation sound less like a tiny robot password.
Tiny robot password rejected. Scientific explanation accepted.
The class repeated the sentence slowly. The numbers stayed in order, and each number kept its substance. If the order changes, the meaning changes.
That is why ratio language must be precise before the math gets bigger.
Sera placed 6 hydrogen molecule tokens in the middle of the table.
Now we will use the sentence as a prediction tool.
For every 2 hydrogen molecules, 1 oxygen molecule reacts, and 2 water molecules form.
So the known amount is 6 hydrogen molecules.
6 is 3 groups of 2 hydrogen molecules.
Then each group needs 1 oxygen molecule.
Multiplier detected. 3 ratio groups.
Good, if the hydrogen part is multiplied by 3, every other part must be multiplied by 3.
1 oxygen times 3 gives 3 oxygen molecules.
And 2 water times 3 gives 6 water molecules.
So 6 hydrogen predicts 3 oxygen and 6 water.
The ratio stayed the same, but the amounts got bigger.
Exactly, prediction is not guessing, it is using the relationship.
Scientific forecast. 6 hydrogen molecules require 3 oxygen molecules and produce 6 water molecules.
That forecast sounds much more confident than my breakfast forecast.
The class checked the tokens. 3 matching ratio groups sat on the table, each one complete. If one group is correct, 3 matching groups are still correct.
That is proportional reasoning, multiply every part by the same factor.
Sera moved the molecule tokens into 3 neat rows.
Before we multiply anything, we ask one guiding question.
Which part of the ratio is the known amount?
Last time, the known part was hydrogen.
6 hydrogen matched the coefficient 2, so we made 3 groups.
But the problem might start with oxygen instead.
Known amount changed. Ratio relationship remains active.
Exactly, the ratio does not care which part we start with, as long as we label it correctly.
If we know 3 oxygen molecules, we match that amount to the oxygen coefficient, 1.
3 oxygen is 3 groups of 1 oxygen.
Then the hydrogen part is 2 times 3, so 6 hydrogen molecules are needed.
And the water part is 2 times 3, so 6 water molecules form.
Good, the guiding question prevents a common mistake.
Do not attach the known number to the wrong substance.
So the first move is not math, it is reading carefully, dramatic but fair.
The table now showed the same complete groups, reached from a different starting point. Different starting amount, same ratio relationship.
That is why coefficients are powerful, they let us move from any known part to the matching amounts.
Mina pointed to the 6 water molecule tokens at the end of the table. Can we start from the product side and work backward?
Yes, the ratio works in both directions if we keep the labels attached.
The balanced equation says 2 water molecules form for every group.
So 6 water molecules are 3 groups of 2 water molecules.
That means the multiplier is 3 again.
Reverse check confirmed. Same multiplier detected.
Now apply that multiplier to the reactant parts.
2 hydrogen times 3 gives 6 hydrogen molecules.
1 oxygen times 3 gives 3 oxygen molecules.
So 6 water points backward to 6 hydrogen and 3 oxygen.
It feels like solving a mystery, except the clues are tiny balls.
That is a good image. Backward reasoning checks whether the amounts are consistent.
Consistent means the numbers fit the same ratio without contradiction.
The class read the table forward and backward. The groups still matched. Forward or backward, every complete group is 2 hydrogen, 1 oxygen, and 2 water.
That is the power of a reaction ratio. It connects all parts of the reaction at once.
Sera placed 1 tiny molecule token beside a much larger scoop of tokens.
Now we need one careful bridge from particles to laboratory amounts.
Because real reactions have far too many particles to count one by one.
So chemists use a counting unit called a mole.
Like a dozen means 12, but a mole means a huge number of particles.
That sounds like the most dramatic counting word in science.
Mole identified, counting unit for atoms, molecules, or formula units.
Good, a mole is not a mass by itself. It is a way to count particles in large groups.
So the coefficients can describe moles too.
Yes, if the equation says 2 hydrogen molecules to 1 oxygen molecule to 2 water molecules, it also says 2 moles hydrogen to 1 mole oxygen to 2 moles water.
The ratio language stayed the same.
Only the counting size got much bigger.
So we did not abandon particles, we upgraded the counting package.
Exactly, first understand the ratio, then use the mole to carry that ratio into real lab amounts.
Concept bridge complete. Particle ratio becomes mole ratio.
The tiny tokens and the larger scoop now pointed to the same relationship. Small count or mole count, the coefficients still compare matching amounts.
That is the key. Moles help us scale the same reaction ratio without changing its meaning.
Ben reached for the small scale, but Sera gently covered the display.
Not yet, the coefficients can talk in moles, but they do not talk in grams directly.
So 2 hydrogen does not mean 2 grams of hydrogen.
And 1 oxygen does not mean 1 gram of oxygen.
Correct, grams measure mass, and different substances have different molar masses.
Molar mass tells how many grams are in 1 mole of a substance.
So grams need their own bridge before they can enter the ratio conversation.
Procedure detected. Grams to moles, mole ratio, then moles to grams if needed.
Beautiful, the ratio step happens in particles or moles.
If the problem gives grams, first convert those grams into moles.
Then use the coefficients to compare moles.
After that, if the answer needs grams, convert the moles back into grams.
So grams are welcome, but only after they get a proper ticket.
Exactly, moles are the bridge between the particle ratio and the mass we measure.
Warning saved. Never treat coefficient numbers as gram numbers.
The class left the scale on the table, but now it had a clear place in the path. Particles explain the ratio. Moles carry the ratio. Grams need molar mass.
That sentence will save you from many stoichiometry mistakes.
Sera wrote the balanced equation one last time, then stepped away from the board.
Now the coefficients can speak clearly.
They say 2 hydrogen molecules react with 1 oxygen molecule to form 2 water molecules.
They also say 2 moles hydrogen react with 1 mole oxygen to form 2 moles water.
But they do not say 2 grams, 1 gram, and 2 grams.
The grams have to wait for molar mass very politely.
Final rule set. Keep labels, scale every part, use moles before grams.
Perfect, if the known amount changes, choose the matching coefficient first.
Then find the multiplier and apply it to every other part.
Forward or backward, the same ratio connects the whole reaction.
So the equation is not just balanced, it is useful.
The coefficients started talking, and apparently they had a lot to say.
They did. A balanced equation gives a relationship, not just a decoration.
Reaction ratio complete. Next challenge. Use the ratio inside a full stoichiometry path.
The molecule tokens stayed in complete groups across the table. Particles explain the idea. Moles carry the ratio, and grams join through molar mass.
That is the bridge from a balanced equation to real chemical amounts.